In this lecture, we will deal with the transient vibration analysis of a single degree of freedom system. Of course, a single degree of freedom system is essentially where one coordinate, typically either x or theta, is used to describe the oscillations of the entire system. Now, basically up to this point in the course, we looked at the case where the force and function on a single degree of freedom system was harmonic or periodic. So, in other words, the differential equation took the form mx double dot plus cx dot plus kx is f naught sine omega t. In all harmonic excitation problems, the force and function essentially ft essentially takes that form of an amplitude sine omega t. And of course, we can solve for our displacement using some of the equations that we derived before. For instance, kx on f naught Now, when your force and function is harmonic, the solution is relatively simple, one. But two, it's appropriate for many practical situations. We saw, for instance, that a rotating unbalance creates a harmonic excitation. And in some cases where the base or support motion is sinusoidal in nature, we can essentially model the system as a harmonically excited system. However, there are a class of problems or really many engineering systems where the source of excitation may not be harmonic or periodic. You can consider, for instance, the impulse forces generated due to the pistons firing in an engine. You don't really expect that to be a harmonic sort of excitation. Or maybe the ground vibration due to an earthquake, or perhaps the oscillations that ensue when a car drives over just a single speed bump but then drives directly on a flat road after. So basically, in cases where ft is not equal to f naught sine omega t, or your force and function cannot be represented as a simple harmonic excitation source, then we can't expect the response to be able to be determined from expressions such as these shown here. So the task we have at hand is really, we want to be able to say that, well, if we have an equation of motion of the form mx double dot cx dot plus kx is equal to ft, where ft can be any arbitrary excitation. Well, how do we determine the response? How do we determine the response xt? Because again, it's not going to be equal to this simple formula that we derived for harmonic excitation. Well, to determine, well, firstly, we would have called the case where ft is equal to f naught sine omega t harmonic vibration problems. In the case where ft can be any arbitrary sort of excitation, what we do is we call those problems transient vibration problems. And there are two approaches to solve transient vibration problems. One is using the Laplace transform. and the other is to use something called the convolution integral. Now in this lecture, what I want to do is I want to focus specifically on the Laplace transform. In the lecture prior to this lecture, I did a review of the Laplace transform in some detail, and really you should look at that video in its entirety before you proceed with this piece of study. Now let's think about it qualitatively for a second. When we had a harmonic excitation source of f0 sine omega t, we got a response. Xt was capital X sine omega t minus phi, right? So the excitation source was harmonic, the response was harmonic. If we are going to have an arbitrary function ft that is not equal to sine omega, f0 sine omega t, then we can't expect xt to be harmonic. The response is going to be aperiodic as well. Aperiodic just means that it's not going to be a periodic function or a harmonic function. So our question again is really for any arbitrary excitation source, how do we solve for xt? And we'll be concentrating on that Laplace transform. The Laplace transform, before we get into the details of it, has this unique sort of advantage where you're able to take your initial conditions into account directly, and it makes solving differential equations very easy. Now, how does it take the initial conditions into account directly? Well, you just need to review that previous lecture and recognize that if you take the Laplace of, let's say, xt, we know we'll get xs. But if we take the Laplace of the derivative of xt with respect to time, or x dot t, then we get xs minus x0, where x0 is your initial displacement. And if we were to take the Laplace transform of the derivative of derivative of x with respect to time twice, then we'll get s squared xs. And again, you see the initial displacement popping up, but we also include the initial velocity as well. And it's really because that those initial conditions are incorporated into the transforms of the derivatives. It makes it such an easy tool. The way I'm going to teach this aspect of the course is really through a series of examples. Now, to apply the Laplace transform, there are basically 4 steps that you're always going to take. Step 1, derive the equation of motion. Step 2, apply the Laplace transform. Step 3, solve for the transformed variable, and the transformed variable is just going to either be capital XS, or if you're dealing with a rotational system, capital theta S. And 4, solve for the response by using the inverse Laplace transform. Might have remembered that L of xs, or L inverse, sorry, of xs is equal to xt. So throughout the examples, we'll basically be applying these four rules.